Okay, keep your questions. Grant did, like you said, Grant covered like a ton of material there. There's one or two topics in there. We'll see if you manage to hit a topic that I can't actually go deep on. There are one or two, and I'm not going to tell you what they are, so ask me anything. Most of it in there I can field questions from. I do want to just sort of two or three extras real quick to add on to the presentation we just watched. I mentioned this in the room here while we were watching it, but logical replication, boy, there's a lot of animations in this slide. This is now shipped, the logical replication. I just wanted to point that out. We do now have outbound logical. Now, as of today, it doesn't have PG. The extension called PG logical is not currently supported on Aurora Postgres yet. So but the native built-in sort of publish and subscribe logical replication, that is out. Is it in preview or is it GA? I think it's GA. Yeah, I think it is. Sometimes I've been real busy with a bunch of other stuff and I haven't paid super close attention. So that was one. Another thing that he didn't mention at all is database activity streams, but this is another thing which is also now out. I'm not going to talk about it a ton. It's a cool product. It's kind of designed as like an auditing solution. There is also an extension called PG Audit, which we do support as well. What PG Audit will do is it's another auditing framework that you plug into Postgres if you need to sort of know whenever certain events happen in your database. PG Audit puts all that information in the Postgres log. It's a tool that's pretty well established in the community, been around for a while. This product, Database Activity Streams, is a little bit different. It sits outside of the database, and rather than putting in the Postgres log, as you can see in the illustration here, it's pulling the information and putting it into a Kinesis stream. And really, this database activity stream product, one of the big driving use cases for this was integration with some like widely used third-party solutions, like they mentioned McAfee on here. But there are some customers who have especially for something like auditing, they have existing relationships. You have a certain partner they work with who locks up all the audit logs, and we wanted to support that. So that was a piece of this as well. You can read more about that, look it up. I just wanted to mention it and get it out there. Now, Grant talked about vacuum improvements. This was something that I just realized that I wanted to mention. He talked about the Aurora bulk prefetch that we were doing. By the way, prefetch is kind of a cool thing in general that Aurora does and something to be aware of. You can bump into prefetch in other places too. You'll know you're hitting prefetch. You'll see a distinct wait event for it when prefetch is happening. So what Grant did not mention was there's another improvement as well in Aurora, which is that in Aurora we've changed the auto vacuum, some of the default values for some of these parameters, and probably there's room for improvement in RDS Postgres in this area as well. The thing with these parameters is that, like I said before, we're very rigorous about when we choose to change a default value. Like, if we're going to change a default, we want to know that it's not a good idea to change a default if it like kind of helps 90% of the time, but then there's 10% of our customers where it gets really bad. In those cases, the 90% of customers, it's almost like Grant said about the explain plans. Like stability is often more valued than squeezing the last little bit of performance. If there's a risk that, I can squeeze 1% more out, but maybe in this case over here, the thing just totally tips over. I'd rather just have predictability and have it not fall over than have get a little bit more performance and not fall over. So with that mentality, we're very rigorous about defaults. We spent a lot of time validating this on Aurora, and we found that we could do this. And so changing these two settings makes auto vacuum a lot more aggressive. Just to show you real quickly the impact of that, something that I did a while ago was that I ran, I did a simple benchmark where I set up PG Bench. And there's a simple tweak that I did to PG Bench, all right? I took, in addition to the standard stuff that PG Bench does, I made a little script that just did a sub-transaction. So it did an update to the accounts table, but it did that update inside a sub-transaction. And the reason or the effect of that is that when you start so you know what a subtransaction is. You know what a transaction is. A subtransaction means that I have like something inside that can be committed or rolled back without rolling back my entire transaction, right? So if I hit an error, I can just roll back that one SQL command or those two SQL commands, but I don't lose all the work that I did. Well, in Postgres, when you start a transaction, you need an identifier. It's called a transaction ID. We've talked about this several times. When you start a subtransaction, you also need another transaction identifier. So the impact of this script was that I dramatically increased the rate at which I was just needing new transaction identifiers. And what I was curious about was if Vacuum would be able to keep up or if a database would wrap around. So I started with a brand new database, pristine, spun up a new database, and then I just ran pgbench with this additional little tweak. And you can see I did custom script at 1, the regular benchmark at 2, and then just defaults. That's all I did. When I did that, what happened was RDS Postgres, let's see here, do I have a, I don't, it's down at the bottom. So RDS Postgres, these are the XID graphs. The other thing I should mention is that I also tested a matrix. So I did 3 different instance classes, ranging from a large to a 16x, and I did 2 different versions. I did 9.6.8 and 10.4, both. I just wanted to see if there were any differences. So I did both versions on all 3 instance classes. So I had 6 different Postgres systems, 6 different Aurora systems, just to compare, right? Well, what happened is every single RDS system wrapped around. Went from brand new to wrap around, I believe, within a day. I have the timings at the very bottom. So this was the output from the run. When you see the word finish run, that's when it wrapped around. So it was a couple days for some of them. But for some of them, like this guy right here, wrapped around in 5 hours. Which is the 16x. The 16x's, they wrapped around. And if you look at what the XID graphs looks like too, you can kind of see it. It's kind of funny. So this is the CloudWatch graph that shows you the how many transaction IDs you've used. This is 2 billion, and that's where you wrap around, right? And it's just like a straight line, shoop, right up there to 2 billion, and then that system went right down. Now Aurora, on the other hand, again, I didn't tweak the vacuum. This is with the default vacuum settings. Exact same workload, no difference. This was all scripted. So I mean, literally, I just like ran a script and it provisioned the servers and ran the same thing everywhere. And Aurora was a different story. On Aurora, there were two of them that wrapped around. It was by instance class. Let me find it. Where is it at? It's up toward the top of this whole section. Right there. So on Aurora, the R4 large and the large and the 4x never wrapped around. And AutoVacuum was able to keep up completely with the default settings. Even with this kind of like insane, I was allocating transaction IDs as fast as I could. And this is what it looked like. This is for the large right here. And this, by the way, you'll see this you'll see this in CloudWatch. This screenshot is from the operator console view, right, of the same CloudWatch metric that like support would see. But this shape is really common. You'll see the line will go up in 200,000. The default settings are that 200,000 is where vacuum kicks in. And you can see there that it just kind of like, it goes up to 200,000 and then it drops down. And that's when vacuum finished and was able to push it down. Back up to 200,000, drops down. So that's what it looks like. And it kind of kept going down. It stayed stable. So you see that vacuum was able to keep up with the default settings. I think that's worth mentioning, that's just another improvement to vacuum that we've done in Aurora as well, after like real careful work there. All right, one more section I want to talk about with Aurora where I go just a little bit deeper than what we initially talked about. And then after this, I'm going to use this as a launch pad to do a little bit of whiteboarding. And this is sort of the area of backup and crash recovery. First thing, just to supplement one other thing that we talked about in the presentation. Now, Grant had this little offhand comment that he made at one point that you want to be multi-AZ so you can fail over faster and have higher availability. That might be like the understatement of the day. We treat, not that we treat it, it behaves very, very differently when you don't have any readers and you only have a write node, a writer node, or a read-write node. So if you only have a read-write node, if there's some sort of a problem, that whole read-write node has to be replaced. There's nowhere to fail over to. It can take on the order of a couple of minutes for that whole process. If I have to spin up a whole new EC2 box, and I have to spin this one down, and then I have to do all of the things that need to happen there, that can be a very long. And not only that, but the thresholds for detecting a problem are more generous. And there's some reasons for this in the way that it's engineered. But what that means is that if you only have a write node, a writer node, it's going to wait a little bit longer, partly because of the cost of replacing it, right? It's going to wait a little bit longer before it really decides, okay, if it's just hung for about 10 seconds, like if a write just hangs for 10 seconds, like we're not going to kill it. We're like, well, if it might come back like in 2 seconds. It's completely different once you even have a single reader node. As soon as you add your first reader, now it's a whole different ballgame because now you can do failovers. And so once the reader is in the picture, even the logic that does the health checking, it takes a different path. And it's like, okay, well, you know what? Now I'm going to really, really prioritize making sure that this thing is really up and running and healthy. And it's not going to let that thing hang for, like, say, a minute or something like that. Like, it'll be in the order of seconds. It'll absolutely be in the order of seconds that if there's an issue, that you'll see a failover happen, and you'll see that reader get promoted up to a writer if that's necessary. So it does make a really big, if availability is something that's important to you, and if making sure that your system is accepting writes and accepting reads and accepting queries, and you're running on Aurora, you do want to make sure that you have a reader. And if you're troubleshooting stuff on Aurora, it's kind of helpful to know that you might see things looking a little different if you don't have any readers there. All right, borrowing a couple of slides. This is the part I want to start digging a little bit more into Aurora. This is a slide that just kind of talks about the backup process in Aurora. And this is something I pulled from one of the MySQL decks, but it's about the storage nodes, and it all works the same. The important point, let me see what my next slide was here. I think one of the important things I want to say about you start thinking about Aurora and Aurora Storage. All right, now they have these segments. Each segment is going to be 10 gigs, right? So we're backing up each segment, and they're going to sort of pull each individual block and push the blocks out to S3. The backups that we're doing in Aurora are continuous. They're different from when you're in RDS Postgres. What happens is you have to take a WAL file and copy that file to S3. And what that means is that you can't start copying the file until the file is complete. You don't want to do a partial copy. So that's one of the reasons that we have a 5-minute, we say it'll be within 5 minutes. And if you watch your, there's a metric for this. If you watch that, you can see that it'll kind of vary. Sometimes it's 30 seconds, sometimes it's maybe 2 minutes since the last WAL file went up. And that's your sort of like your window of loss if everything kind of disappeared, if you had to lose the host completely. You might go back 2 minutes if you had to go out to the S3. That's a different picture on Aurora because it's sort of continually pushing the stuff off, and it's able to keep up much better. It's also able to be continuous. It doesn't have to wait for anything to be able to push the change records out to S3. When we do a recovery, we're able to sort of roll these things back. We also have, this was also something, I don't know if Grant touched on this, but there's something called backtrack. And what backtrack is, so backtrack is going to tie right back into the backups, all right? So what backtrack is backtrack is kind of the ability to rewind your database, and basically, and it's so it's the ability to do a rewind only within sort of a small window of time that you control, right? It's within a small window. So you're not necessarily going to go like 3 months back, but you could go like an hour back. And it doesn't have to go to S3, it doesn't have to go to the backup system in order to pull that data. It's able to just pull the blocks back out that it needs, and then it's able to roll forward the blocks, roll forward the changes very quickly, and then you sort of see the illustration here, right? It's able to sort of back up to T1 point in time and then start a new and then restart the database there, and now you're on the blue line. And then you can do it again at, say, point in time T3. The reason that they have this T2, so the way that backtrack works, you're not losing any history, okay? So this is, we'll just say this is 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock. It's a little easier for me to do verbally. So what happened here is the user at 2 o'clock, they realized that something bad had happened and they needed to rewind. So at 2 o'clock, they said, OK, rewind it. I need to go back to 1 o'clock. So what happened was Aurora, the Aurora Storage, it undid all the changes, and it restored the database to a state it was at 1 o'clock, and it did that at 2. So then we start a new version at 2 o'clock. Now, when you get here to 3 o'clock, in this example, let's see, they keep going, and at 4 o'clock, they do another rewind to 3. You could still rewind back to 1:30, and that would put you back on the green line, right? They don't erase this history from 1 to 2 when they go back to 1. All right.
Can you rewind to T1, export data, and then just go back to T2?
You should be able to, yeah. I mean, you would go to like a time, yeah, you'd go essentially right to there, right before you. Yep. Oh, okay, I'm sorry. Let me just rephrase the question, since we're recording. The question was like, if you could rewind and then go right back to the point where you rewound from. And yes, because as long as you're not losing that green bar, essentially what you do is pause activity on the system to make sure you have a clean point, and then you'd go back, export your data, get your data. Now, I mean, if that's what you were doing, it would probably make more sense to use like a fast clone or to do a point-in-time recovery to a different system. If you already knew that you're just doing an export and going back, there's probably other strategies that would make more sense. But yes, that should work. So that's backtrack. How does backtrack work under the covers? It's doing the same thing with those backups. The only difference is that it's keeping all the log records on the storage nodes so that it doesn't have to go to the backup system. All right, there's a slide in here on crash recovery. And then there's going to be one more slide about crash recovery, and I want that crash recovery slide to be kind of my launching point to start whiteboarding a bit on a couple other Aurora scenarios. So, oh wow, and it's already 11. OK. All right, so I'm going to skip this slide and just jump straight to the next one. There's a couple of concepts that we have in Aurora, and this is where I'm going to go. I think we didn't introduce some of this terminology, but I really want to because it's really useful to know. So a couple of things. I've been throughout this entire week, I've been giving a lot of examples where I say 1 o'clock, 2 o'clock, 3 o'clock. You know, like rewind the database to 1 o'clock, or there's a read replica, and the database, the master might think that it's 2 o'clock, but the read replica is 1:59. Now, in reality, the database is not tracking timestamps. The database actually has another thing, which is called an LSN, or a logical sequence number. And this is kind of a concept that's common to a lot of relational databases. That you have this, we've talked a lot about transaction IDs, and the transaction ID is sort of one counter. The LSN is like the other lower level, really critical, like clock or counter that's always moving forward in the system. LSNs are not 32 bits, thankfully. They're much bigger than that. LSNs are always moving forward. And the LSN, and this is really important. In RDS Postgres, in regular Postgres, the LSN is super simple. It is, if you look at like the LSN from one of the catalog views, what the LSN actually is literally just an offset into a file. It's just an address. Like you take the first half of the LSN and it tells you the name of a file, and you just open that file. You take the second half of the LSN and you just go to that offset, and that's literally like the wall record you need to replay starts on that byte. So the LSN points to where you are in the redo stream or in the wall stream. And what that means in community Postgres, there's some implications of that. It's, first of all, if you have an LSN, it's super easy to know what to do with it, right? You can go straight to a log record. That LSN just references a log record. It also means that they don't monotonically increase, right? Like if you have one LSN, the next LSN is going to be dependent on the length of the log record that one points to. Make sense? So the LSNs could go from like 100 to 230 to 250 to 290 to 400. And that could be how LSNs they're kind of jumpy like that in Postgres, in RDS Postgres. It also means, though, on the flip side, if you look at two LSNs, you know how many bytes of wall are in between them, because you just subtract. It's very simple. You don't need to do anything extra. So it's an interesting approach. When we built Aurora Postgres, well, I wasn't here at that time, but they redefined the LSN of how the whole thing works. And in Aurora Postgres, the LSN is not a physical address. That's just kind of important because if, like, for example, you have some sort of a query that subtracts two LSNs and you're assuming that tells you just like how much data was changed, that won't work on Aurora Postgres. I don't think that, well, actually, I'm not sure whether it just monotonically increases like 1, 2, 3, 4, 5, or whether it's different, but I know for sure it is not the offsets. So that change can become significant at some point in time. And when you ask for an LSN in Aurora Postgres, you're going to see like the Aurora idea of what the LSN is. It doesn't try to do any translation or make it look Postgres-y. Okay. Now that in Aurora we do have an LSN. It's the same sort of thing. It's identifying some, where you are in the stream of changes. Although, and we could maybe call it, it's not really wall, because in Aurora it's not, it is a similar format to the wall records, but it's not identical. All right. We kind of started with the wall records, and so this is another really interesting thing about Aurora. If the way that Aurora works, we've talked a lot about those storage nodes. There's Postgres code running in that storage node and MySQL code. All right, and this is also, by the way, you can pull down the paper that we wrote about Aurora that went into the ACM journal, like the public paper, and you can get all of this right out of there too. It's a great paper to read. Man, I should mention that right at the top. If you want to go deep on Aurora, one of the things I always tell people is read the ACM paper. It's not super long. It's like 6 to 8 pages. It's very technical, and it's a great paper. And it's public too, like anybody can get it, anybody can read it. You can just search for it on the internet. So that paper talks about how they started with MySQL code and they worked from there. And yeah, the storage nodes, we've talked about the Aurora architecture of how the storage nodes, so it sends like the wall record is basically sent over the network to the storage node. And then the storage node, do I have a picture? I don't think, oh. At one point, I had a picture. Hang on. There's a really good picture. I do have it. I just left it in the middle of the deck when I thought that I was going to give this presentation myself. This is a nice picture. So this was the one that Grant used, which is like super simplified, right? From the talk that we gave today. I personally like this one a little bit better. It's different formatted, but it has a little bit more detail too. And this gives you, it's the same stuff that you saw on the other slide, really. It's just not animated. I think Grant likes doing animations. And they're nice. But they give some of the different steps. So what's happening here is that sometimes we call this the head node. That's kind of like just sort of an internal lingo that we use, and we call this the storage node. So if you hear somebody say head node, what they're talking about is here. And that's largely operating like Postgres. I mean, there's still like, you'll hear more and more things, the survivable buffer cache, the cluster cache management. There are places on the MySQL side, I think they've made even more changes to the engine itself. But that still largely operates like a database server. The storage node is largely operating like a storage server, but it has database code. It has Postgres code. We call that, the part that kind of has the Postgres code, we call it a page writer. That's kind of the name that we usually use for it. The page, it's the page writer is the part, it's kind of this module that is based on Postgres code that does recovery, right? Because Postgres recovery code, what does it do? It reads a wall record, it applies it to a block. So that's the piece of code that you need in the storage node, just logically. Make sense? So you take that code from MySQL or from Postgres or wherever, and what does that code do? Well, it writes the changes to the block. What's the name for a block? A page. So it's a page writer. Makes sense? That's why it's called that. That little piece of code, that little bit of Postgres code, that is the one little bit of code that actually lives in the storage node. So these log records, which we had to build a network protocol and do some things like that, but the information in here is the same information that would be in the wall record, because we're doing the same thing. We're taking a change record. It's the same thing that happens when you do crash recovery on a database, that you have to replay these records that were in the wall stream. That's what we're just doing it all the time. So it's the same information that we need comes through the log records, and this is where they talk about the C. Now this queuing bit. There's no Postgres code here. All this is doing is just taking those records and putting them on the disk so that this guy isn't blocked. Get him unblocked, make the write path super fast so he can keep moving. It's this piece, the coalesce, and they say data blocks here, but blocks, pages, same thing. That's the piece, this number 5. We call it coalescing, but that's the piece where you actually have some database code, because that's a piece that reads the log record and applies it to a data. Now, the reason we call it coalescing is the other thing is that what we're actually doing is that we actually have kind of like this stream. These data blocks are not stored in a different separate place from the log records. I think this is kind of neat. They're all stored together. So what it's almost like log. There's a thing now of like log structured storage. There's some vendors making storage arrays. I want to say at one previous company I worked at, we had some Nimble storage. I think they do this, for example. They're one of the vendors doing this. There's a bunch of them out there that are doing log structured storage. And it might be a good parallel. I mean, what we are doing is that we have a single place, and it's kind of like that. It's a stream of change record, change record, change record. And at some point in time, what we do is we need to so we have to keep the full block that's back at the beginning, because if I need to reconstruct a page, I'm going to start with the full block, and then I'm going to move forward. We call it coalescing, because what we're going to do is we're going to take that full block, apply all the changes to it, and then just write a new copy of the full block down. Once we've done that, right at that point in the log, it's now safe to take all the old log records, and once you've archived them off to S3, you can remove them out of memory. You don't need to keep them on the storage node anymore. And once you know that you also have to be sure none of the reader nodes are going to need those old blocks as well. So, slide 19. That's almost, so that gets into this right here. So now we're here. All right, this little line you see how it says a list of log records? That's the line that I was just describing. That's the series of log records that Aurora has in the storage. And each one of those records has an LSN. And that's what we also call it in Aurora. An LSN identifies a log record. All right. Now, in Aurora, so we've got this series of log records. Now, there's actually some full blocks in here as well. And we occasionally do coalescing, and we get new full blocks in here. There's a couple of important sort of pointers, and that's what this slide is actually pointing out. I love that they have this slide that they get to this level of detail with our customers at reInvent. I think that's awesome, and that's what we need to do now. I'm going to point out a couple of them. One thing that you'll notice is these gaps. The reason that we have gaps is because, remember what we were saying earlier, or what Grant was talking about, how Aurora will just kind of like batch all those updates and just push them down as fast as it can, right? They don't come in order. So what you can totally have is you could have a couple of records coming down, but you might still be waiting for the records that were in between. And this is totally valid. Eventually these other records will come, and then things will be fine. But they don't need to come in order. However, if there is a crash right at this instant, and we have some gaps in here, well, now we need to, after the crash, we're going to start the database back up. And in order for the database to start up, the database needs to know, what's the point in time where I'm starting. Am I starting as so if you crashed at 1 o'clock, are you going to start as of 12:55 or 12:58? How much data did I lose and how much data do I have? Was it 2 milliseconds, 10 milliseconds? What was it, right? Now, keep in mind, when I talk about losing data now, I'm not talking about losing any data in your database. This is just when I'm going to lose the bits on the disk, because there will be some data that disappears. It's going to all be uncommitted data, right? Because there's always the uncommitted data. We certainly don't wait for the commit to put the data on the disk. We're continually pushing data down to the storage and down to the disk. And then commit is just the point where you have to pause for just a moment. And when your application says commit, we don't acknowledge the commit until we know. And this is what we're going to come to actually. So now you get to sort of see the guts of what a commit means inside of Aurora. Okay? Inside of Aurora, when you want to do a commit, what you need to know is that if there's a crash, that commit is safe. So what does that mean? Well, let's talk about doing the crash recovery, and that's what this slide is all about. So if I have all of these gaps, the point right before the gap, that's the point where I have complete data. So basically, this is the point in time where if I go after this point in time, this would be corrupt because I'm missing something. I'm missing something, and I replayed this other log record. That would corrupt my disk. So this right here, we have names for these things. We usually use the acronyms, but we use them all the time. And what we say here, this is the volume complete LSN, all right? So this point is the point where it's complete, meaning we're not missing any records. However, that is actually not the point at which, all right, so that we have explanations over on the right. They say that's the highest point where all the records have met the quorum. But that's different. Right. OK. For the consistency point, we track one more thing as well. We track something called a consistency point LSN. That's right. And the consistency point LSN is just saying the commit record. Go to the last commit. Because basically, what you wind up with here is if this guy was a commit, these two records ahead of that commit, we don't really need those anyway, right? Because there were no other commits after this one in the stream. So, or at least none that there could be a commit here. What would that mean if there's a commit here? What it would mean is that the commit had gotten down to disk, but it had not yet been acknowledged to the client. Because this comes back to what does a commit mean in Aurora. So in Aurora, we don't just have to so commit records are different. Other things just need to get to the disk and they're durable, right? But a commit record doesn't just need to the disk. The commit record needs to be consistent. So when you commit data in Aurora, it'll actually pause and make sure it's recoverable to that point. And because it has to be recoverable to that point, and then you can acknowledge it back to the client. So if there's a commit here, that just means, OK, we're in the process of committing, but we never sent that message back to the client. We never told the client this data is committed. The client was trying to commit something, and the system crashed while the client was trying to commit. That's what it would mean if you saw a commit record out here. But it had not been acknowledged back to the client. Therefore, that commit does not represent any data that was lost. So what happens when you do crash recovery? Here's basically everything gets cleared after the consistency point LSN, or the CPL. So that's this picture here. And this is where I'm going to shift gears. And so we talked about the consistency point LSN and the volume complete LSN, the VCL. But now I want to just go back and I'm going to do a little bit of whiteboarding. And there's two pictures that I want you to keep in your head as I switch over to the whiteboard, okay? The first one was this storage node picture, because I'm going to talk a little bit more about this for a moment. And we're way over. Do I have time for this, or should I just skip the whiteboard? I got to do this. This is like really important stuff. I'm glad to know, though, that I'm not going to not have enough content. Remember when I said that at the beginning? I was like, I'm worried I won't have enough to fill 2 hours. Well, I was wrong. Yeah. All right. The second picture that I want you to keep in your head is this one or this. Yeah, this guy here, sort of. All right. OK. I'm going to shift gears. So what I'm going to do right now is, just to help him out, I'm going to black that out. And I'm going to hop over here and draw on the whiteboard a little bit for you guys. So, all right. Here's where we're starting. We've got, I'm going to sort of replicate that picture. We have a reader node, 2 readers, and a writer, OK? And then what we've got here is, these are, of course, in 3 different AZs, right? And then we have the Aurora Storage that sits in all of these 3 AZs, OK? And what do we have going on here? We have, we talked about this, Grant talked about this a little bit in his presentation, but each, generally speaking, now they're continually testing. So every so often these guys will try to do a read from a different AZ just to kind of check. But I mean, naturally what's going to wind up happening is the reason that they could potentially end up finding it being faster is if they happen to be talking to one particular. So remember, they have 6 copies, but for a certain block, that block has 2 copies in this AZ, right? The block doesn't have 6 copies in this AZ. If both of those copies maybe could see, I can't imagine this happening, but the only thing I can even think of is if those 2 copies of the block were on servers that were just momentarily were really, really busy, maybe it would be quicker, especially with the latencies between our AZs keep getting smaller and smaller. Maybe it'd be quicker to go somewhere else. But generally, local AZ, right? So they each are talking down. Now, there's something that, so we talked about LSNs. I'm going to go back to timestamps for just a minute. But in RDS post, so I think one of the most confusing things about Aurora for a lot of people is so we've talked about read replicas. So is Aurora more like, I don't know, like in Oracle terminology, is it data guard or is it rack? Which one is it? And I actually really think this is a really confusing thing a lot of the time. Is this more like a standby database, or is it more like a cluster? Now, the answer, what I'm going to say, what I'm going to propose, the answer should really, you should always lean more toward cluster. It really behaves more like a cluster in most ways. But there's a couple things. One of the ways it doesn't is that if, in Oracle, for example, with real application clusters or OPS back to 8, Oracle does a thing where it tries to maintain global consistency in a single global image of the database, meaning that all of the nodes are at the exact same point in time. There's this cluster-wide global consistency. It has a lot of sophisticated stuff to do that. It has a global lock manager. It has the global enqueue services that do the locking. It has cache fusion and global cache services. There's a lot that goes into that. In Aurora, one of the things is we have these what we call reader nodes, and then we have the writer node. And the reader nodes, this is different. The reader nodes actually act this is why I think it gets confusing, for 2 reasons. First of all, because we call them read replicas, I think, way too much. They are, but that's the same word that we used in RDS Postgres. And I think that just causes confusion a lot of times, right? in Aurora, and I mean, I hope this is like abundantly clear from the first presentation that it's shared storage. That this guy, this is not the same kind of read replica. However, there is something that is similar, and that's the fact of the lag. There's no concept of lag in Oracle RAC. There is in Aurora. So the writer might think that it's he sees the database, a picture of the database as the database looks right now at 3 o'clock. This reader, he sees a consistent picture of the database, maybe the way the database looked at 257. Now, I hope you're not really going to get that much lag, but this just makes easier numbers to work with, okay? Now, one important thing about that, like when I say 257, that doesn't mean that like some of the blocks from 3 o'clock are here, but they're just hidden. It's completely consistent. As of 257, it's almost like he's traveling back in time and looking at the database. And maybe this reader sees it at, say, 259. Now, how does that work? The way that works, and I think this is kind of one of the really important things to understand, is that in the protocol, the storage protocol, when this guy reads a block from storage, he sends two different things in that message. He first tells what block do I want. I want block number 24, and I want that block from 257. Now, I'm using the times, but you know what's actually it's using, right? The LSN. So we kind of introduced the LSNs. Those LSNs are the things that we're going to use. So each reader has like its read LSN. That's another place where LSNs are going to pop up. And the lag, what's the lag? The lag is the difference from the read LSN to the writer or the current LSN. That's your difference. So it's built into the protocol. And then we had that picture of the storage servers, right? Well, the storage servers are smart enough to understand this, and they can reconstruct a block as of any point in time. Okay? So this storage server, and remember, this storage server might be receiving requests from both the reader and the writer. So the storage server does not have like a point in time. The storage server has all the blocks, right? All the pages with a couple of full pages in there. And okay, so maybe he has a copy of the block from 259 and then one from 255. And he says, oh, 257, okay, I'll start with the 255 block, replay the changes up to 257, and then I'll ship that version of the block up to the reader. So that's what's going on. It's really cool. It's very smart storage that it's able to do that, right? So that's what's going on there. Let's see, picture number 3. So that's the block and the time. That's the storage node. It reconstructs the version. All right. So then that gets into the next question. See, I have the picture I want to draw. I don't remember the question or the reason. So the next thing, because I think that the question people sometimes wonder is, what if I have like a long-running transaction on the reader, is that going to like somehow block this reader from advancing? Okay, the question under the question here is a replica lag is like the hot topic of the day with Aurora. I mean, I've been getting so many questions about like, I just want to understand reader lag on the readers and like, why is it happening? What's going on? And that's the thing I want to get at. So one question that has come up in the past when we've talked about this kind of stuff with people is they're like, okay, well then it must be that like if I have a transaction going on, I can't let this thing advance because I still need to see the data from 257, right? That's not the way it works. So in fact, we're still relying on the Postgres MVCC for all of that, right? So we can let this guy, this is an LSN, this is different from XIDs. There are still XIDs, there's still vacuum, there's still multiple versions of rows in every block, right? All of that's there. So we can still let the thing advance. So what does that mean? That means now, what about vacuum? So in Aurora, the way Aurora works is we do not let you disable hot standby feedback. It's it's turned on, and it cannot be edited. It can't be disabled. And that's basically what happens. And then also in addition, Aurora is not using, it's not actually Postgres code that's even doing the hot standby feedback, to be honest. There's Aurora specific code. There's something called a client-side daemon that's running, that's in here. And actually, it's just like I was saying, the LSNs are kind of different and Aurora specific. There's an Aurora specific mechanism for doing the communication between the nodes. So that's a piece of Aurora specific code. But it's the same mechanism in that, so basically what happens is, I've got a report running over here, okay? And let's say I started my report at 2:30. So you got this report running over here, and he's connected to this reader, all right? Well, what happens is we have this kind of global state over the whole cluster as well, where we're maintaining what is the oldest open transaction. And so we're going to track that. And we will know that the oldest open transaction is 2:30. And then what will happen is vacuum running on the writer. Vacuum is always going to have to run on the writer because only the writer can change blocks. He's going to track that, which is global at the cluster level of just the oldest open transaction. He just vacuum will make sure I'm not going to remove any rows. So he's going to leave all those rows on the disk until the report finishes, and then vacuum can go down and clean it up. So, pros and cons. All right. The great benefit of this is that we have no lag from having open transactions. What are the cons? Same thing. And by the way, this applies to having read replicas with hot standby feedback enabled too. The con here is, and you have, like I say, exactly the same thing with cross-region replicas or any replica with feedback. Remember when we talked about hot updates, how that longest open transaction can sometimes have a surprising impact on table growth and index growth, right? And that applies here as well. So table and index growth. Basically, it means that it's very important to watch that oldest open transaction. So where did I want to jump to next? Yes, one more quick thing. What can cause replica lag? So this doesn't. Then the big obvious question that's next is what does, right? Because it clearly is happening. Well, there are actually, there's the easiest way to illustrate this in Aurora Postgres. I'm going to list a couple of things out in a moment. But before I do that, I have just two more things I want to talk about. So what does cause replica lag? Well, the first thing is something called hard conflicts. So what's a hard conflict? Back up here, I've got my reader and I've got my writer. All right. So let's say I'm over on say this reader on the right this time. Okay. And this guy opens a transaction, begin, and then he does a select from test, and then he goes to lunch, right? And he forgets to close his window because he was working really hard. Now what happens? Now on the writer, drop test. I think I talked about this yesterday or the day before, right? This is called a hard conflict. So in the Postgres docs, you can look this up. Actually, I don't remember if I talked about this. Did I talk about this yet? No, I haven't. Great. Keyword, hard conflicts. One of the things I think I put in the lab exercises for tonight was see if you can find that in the docs without me telling you where it is. It's a fun one. There's a list. Postgres docs are great. This is one of them. This is a really obvious one. So the thing is, if you're in Oracle, this is there's only two approaches to this kind of a conflict. There's a pessimistic and an optimistic approach, right? The pessimistic approach is that you have locks and you use locking. But these are two totally different machines. And that's called is a distributed lock manager or global locking. Or a DLM is the lingo that people use, who are around this stuff all way too much. We have made the decision to favor throughput and to be optimistic about things like this, rather than trying to at this point in time, put a DLM on top, or a global lock manager on top of Aurora. So what that means is we let this go through. We're not trying, because the downside is, if you want to do locking, what that means is that every single time you do an operation on a reader, you have to check. Like, you have to, it introduces a huge amount of communication between the nodes. It's not impossible to do. It can be done, but it's not cheap, right? And when I say it's not cheap, I'm talking in terms of performance, not dollars. Although it's probably true of dollars too. So we let it go through. We're not doing all of that coordination that's required to, like, again, maintain global state and also have like global locking. So we let this go through because the writer doesn't know. Now, if you ran that on the writer, he would block. That drop test statement, it would just block. And he would try to be getting an access exclusive lock. This is the stuff we talked about yesterday. You need to have that lock timeout so you don't take down your system. Although on a drop table, it's probably not a big deal. So he would block. But if you run it on a reader, and this is, again, exactly the same thing that happened on regular Postgres with replicas. If you run this on a reader, that's still going to go through. So you have a drop record, goes in your wall log. This will go to the storage. And all right, the fun thing here is that Aurora MySQL and Aurora Postgres work completely different. If you're on Aurora MySQL, what will happen in this situation is that this transaction will immediately die. Just be like, he replays the record. Oh, somebody was trying to access a table. Well, too bad for you. Kill the connection, throw an error message out, you're done. Instantly. Postgres is different. Aurora Postgres, what we do is we give it at this point in time is not configurable, though we're talking about making this, actually opening this up and letting customers configure it within some boundaries. Right now, we have it just configured as 30-second grace period. So what happens in Postgres, Aurora Postgres, is if you do a drop, if you do that drop, the record will come. And what's actually going to happen is the record, by the way, will go over the network, right? Because what we're doing is we're sending cache and validation records. We are sending changes over the network directly between the nodes to invalidate the cache or update the cache. And the drop will come across too. So it'll come across the network, and when it gets there, a counter, a little timer, immediately starts as soon as this guy sees that record. He will give you 30 seconds, just in the off chance that you're not at lunch and you were about to finish anyway. He'll give you 30 seconds to finish what you were doing. He doesn't tell you this, but he just does it. As soon as 30 seconds are up, then it kills the session. That's how it works in Postgres. So that's an example of sort of a really obvious thing that can cause the replica to lag behind a bit, right? 6, 7. Oh, these are in a different order. All right, now I'm going to erase this, and then I'm going to actually, now that's kind of like the expected thing, but there's a couple other things sort of expected that we've seen as well. I'll just do this. I won't write all these out, but I'll just kind of go through them. So the common stuff other common things that we see and that we kind of expect to see causing replica lag, and this is important to know about because this is something that's being talked about a lot right now. There's kind of two different things. First of all that we see is for people that are on very small instance classes, our smallest Aurora instance class is the R4.large. And we see people when they run really big workloads on those, that literally the reader just, and what we've also especially seen is that somebody will have, sometimes they run like maybe a 4x or an 8x writer, but then they spin up like a tiny reader because they're thinking, I'll save some money here. Like, that's totally fine as long as you're not actually doing anything on the writer. But if the writer's like running hard, full speed, and if it's it depends again on what it's doing. If it's doing a bunch of queries, that might not be a big deal. But then it depends what your reader is doing. If you exhaust the resources on your reader, I mean, you can exhaust resources to the point where it just can't keep up. So the first thing we've seen is just CPU exhaustion on the reader. So one of the things that we check for is if you have replica lag, and you're wondering what's going on, one of the first things we look at is just like look at the CPU utilization. Was the CPU pegged at 100% for like a little while when it got behind? If the CPU is pegged, I mean, it doesn't prove it, but it's highly suspicious. And and we know for sure that that does happen. And so that's something we look for. Network saturation is the other thing also. So on the small instances. Now there's something different on the big instances. We've seen another thing that's fairly common on the 16x's, the largest ones, which is that in Postgres, there are a small number of operations you can do which require scanning the entire buffer cache for those operations to complete. The really notable ones are dropping a table or truncating a table. When you drop a table, Postgres does not, so Postgres has a buffer cache, right? The buffer cache is all these little 8K blocks, and it's just a cache of the stuff on the disk. Postgres does not maintain any kind of a reverse index that says, for this object, tell me all the blocks in memory that are associated with that object ID. So that's not usually a big deal, because it's rare that you need to do that sort of thing. Usually, it's rare that you would need to do that sort of thing. Usually you're looking for a specific block, and you know the block that you want, and you go looking for it. Dropping and truncating objects in Postgres require scanning through the entire buffer cache, that by itself is not a big deal, but what we've seen is we've seen a couple of workloads, like for example, workloads where you're making heavy use of temporary tables. You're like create 30 temp tables, do some stuff, drop 30 temp tables in a row, and then you get like 100 connections doing that at the same time, and all of a sudden you got 300 or 3,000 table drops right in a row. And that's absolutely something that we have seen take down large readers, because they're trying to replay those. What happens is each time they want to replay that drop command on the reader, they have to scan the entire buffer cache.
So do you record statistics on when that happens?
Can you write that down? That's a good question. Stick it in the chime room, because I want to answer that with everybody, actually, not just here. The other, I mean. So those are the three kind of the four sort of like common expected things that I know of so far for causing lag. There are also like a handful of, there's a couple of bugs that are in the process of getting fixed right now. I'll probably tell you about one particularly fun one later in the lab, because you can actually use it to like trigger a reader restart whenever you want for now, but not for long. Because they've already fixed it, so it's just a matter of time until that gets pushed out. But it's kind of fun to exploit something like that, like on the couple of days you get. It's great for actually kind of studying the engine. So outside of those things, if you see issues of lag popping up, that's where we want to hear about it as of right now, because this is really important and we're looking to improve it. Now, how much lag is okay? I mentioned something there which I hadn't really said before this, which was reader restarts. And that's, of course, the big reason everybody wants to know about replica lag is because they're like, hey, my reader just like restarted itself. What gives, right? That's like the driving thing. So here's a picture that I hope will help with that. So I'm going to draw a line here. Let's see, 2, 1, boop, boop, boop. Okay. 1 minute. All right. So the writer, this is lag. Okay, so that's the writer. And then this is lag. So your reader gets behind by how much, right? This is in minutes, but I've made little tick marks every 15 seconds. This is my most up-to-date understanding of how this works, all right? I had to really throw some people up the wall to figure all of this out. It turns out it's actually really complicated. It's not just like some one number where like, oh, if you get to this number of lag, then you get restarted. Unfortunately, it's not that simple at all. I wish it was. But basically, the way Aurora was engineered, it was designed, I mean, people were trying to think of like clever ways to make it available. I actually think as I've been trying to understand this, I don't know, maybe in a month or two, like this will all become really clear and easy to distill down. Maybe not. Right now, I'm wondering if we over-engineered it, but I don't think so. We're trying to keep systems up. It's just like what I said earlier, like sometimes I prefer predictability over other things, or like I'd love if it was easier to explain. All right, so the first 15 seconds are green. So for 15 seconds, you're like green light. You can have 15 seconds of lag, and as far as I know, like from my reading of the comments and the code and from my talking to engineers, I don't think that we ever like knowingly cause something bad to happen with 15 seconds of lag. After 15 seconds, you start getting into the gray zone. So from the next phase is from 15 seconds to 1 minute. And I'm coloring this blue because this section is generally safe. There's kind of two things that I'm aware of that can cause a restart here. All right. Or I actually would make this yellow if we had a yellow marker. This is like kind of like the caution zone, I would say. Yeah, that's what we're going to do. We're going to call this caution. It's not danger necessarily. Boy, that's unreadable. Try that again. Looked like I was like making artwork instead of drawing letters. All right. The two things there that I know of is that, first of all, so for the caution zone, the storage nodes themselves, if they, I haven't actually seen this happen, but I've seen code for it, so theoretically it can happen. So that supposedly the storage nodes, if they need to throttle or to slow you down or something's going on, like if I don't know the reason. The wording is throttling. That's the word that's kind of like used. Like I said, I've never actually seen it happen on a system yet. But the code says that from 15 seconds to 1 minute, the storage nodes can send a message that will trigger an error condition that causes a reader to be sort of restarted so it can just catch up, right? And that can happen after 15 seconds. The second thing after 15 seconds is there's something called a transport buffer. I believe that's on the writer, I believe. And that transport buffer it's basically like a buffer in memory that's kind of like holding changes that need to get sent over the network to the reader. So basically, this is, I believe, the network throttling case, where like if I don't have enough network bandwidth, right? I probably should just rewrite that. So I'm going to double check that with the engineers too. I think that is I need to find, because I know the message to look for. I should check the logs, because that would be really useful to know. If I'm right about this, then what that means is that after 15 seconds is the point where you can start seeing network-related restarts, because your network is throttled. So what do you do if you're hitting this? That transport buffer, the size of it is just based on your instance class. So basically the answer is you scale up. Because when you scale up, first of all, you get more network. If you're on the tiny, I mean, we don't ever see these issues on our big instances. This happens when you're on a small instance. That's the only time we ever see it. Because as you get to the largest, you get more network bandwidth, and you also have bigger buffers as well. So it's just this tiny instances. And by the way, when we release support for T-class, all of this stuff is going to get even more important, right? Because that'll be coming out. So that's something you want to keep in mind. That's the caution zone. After the caution zone, we get into what I'm going to call the danger zone. All right? The danger zone is from 1 minute to 2 minutes. Okay? Once you're in the danger zone, once you're over a minute, all that has to happen really is you just have to be unlucky. So what happens after 60 seconds, the way Aurora is designed right now is that, so I think and I guess the other really important thing, I forgot to write down this part, but there's a tension, okay, that we're balancing here, okay? When you just have a little bit of lag, the system is designed to favor reader availability, okay? But the more lag that you see, the system begins to try to, because what you're doing that at, you're doing that at the expense of something, all right? And that's why it's a tension. You're keeping your readers up, yes, true, but you're doing that at the expense of writer throughput, right? You essentially, you have to throttle your writer to keep the readers available, all right? And so we're balancing this tension between reader availability and writer throughput. As you get into the danger zone, what happens is now you're getting to the place where we're going to say, look, we can't just we can't stop the writer just to keep your reader available. So at this point, we're going to favor the writer over the reader. Like we can't have both. Either the writer is going to get stuck and the reader will stay up, or we've got to just do a quick restart of the reader and the writer can keep on going. So in the danger zone, we favor the writer throughput. What happens after 60 seconds, and this is the threshold where it changes, is 60 seconds. At 60 seconds, the writer, so you know how you have those feedback messages that tell the writer, well, the writer will start just going ahead and advancing. Oh, and that's where we get into the thing. There's one other kind of really important, we've been talking about LSNs. Every cluster in that global state that I talked about, I forgot to write this on there, but it maintains something that we call the minimum read point LSN. So it's the minimum read point. That means if you try to read an LSN lower than this, so what this actually is, this is the LSN, and so it's the head node. The writer head node is the guy who gets to decide this LSN. And what this is the LSN that he sends to the storage, and he says, okay, this is the oldest LSN that you need to keep. After this LSN, you can go ahead and start back them up to S3 and then clear them off of your disk, all right? But this is the oldest one you need to keep, is this minimum read point LSN, or what we often call it is the MRPL. That's what I've heard the engineering team say a whole bunch of times, is the MRPL. So the minimum read point LSN, that tells the storage node. So what that means, at 60 seconds, the writer will start, it will now calculate a MRPL and it will disregard the reader. So what that means is the writer has given permission to the storage to do cleanup of records that I might still need to read. So once you're in the danger zone, all it takes is you need just to do a single I/O, right? That was a lot lower than it needed to be. Below the MRPL. And if you do a single I/O below that MRPL, you're toast. You're host. The storage will say, I do not have that. Not here. And then you get an error message saying read below MRPL. That is a fatal error, and that immediately triggers a reader restart. 2 minutes. I said I only drew this line up to 2 minutes, and 2 minutes or thereabouts is basically the death zone. How do you like that? Only from the perspective of readers, though. I love this. This is a great graph. I kind of made this up on the fly, but Yes. So once you hit the 2-minute zone, that's where at 2 minutes the code will just say, look, 2 minutes, you can't go past 2 minutes, and regardless of everything else, we're just going to restart this reader by the time it comes, because what will happen on a restart, all it is just like kill the process, restart the process. But when the process restarts, he doesn't have to replay anything. He doesn't have to catch up. It's just like, oh, okay, I'll just take this LSN and start doing my reads from this LSN. So it's like an instant catch up to just like stop the process and restart it. And that's what we're going for. So the idea is that, again, I think that this sort of tension is sort of the key thought, that what we're doing is we're balancing attention between reader availability and writer throughput. And the more that you lag, the more that we're going to favor the writer. All right, that was the end of what I had to talk about today. I hope that is useful.